Oh. What should we do? It is a physical chemistry class. If you want to predict outcome of experiments, the measurements of material characterization, we learn mathematical details about wave nature of electron. And suddenly we decided to do this quantized protons or atoms because they also perform like oscillate with quantum protons. There is a chance that today is the last lecture day. Do not say hurrah. No, last lecture day on this subject on oscillating protons, and then we'll do two other objects. So I'll try to review a couple of previous lectures, overview where we are on the map of the class. Not this one, I have a better one. Well, it's ugly, but it has more information. And then we'll use. We finally we will obtain that a proof that oscillator oscillates, and then it will be done with oscillator. Very, very exciting. On Wednesday, if possible, I'll just skip these things and run into new materials like angular momentum, which will be related to the project that I'm never. So Wednesday will be your day for the lecture, and Wednesday night, the main client of the lab will be Morgan. I saw your request, but if I'll probably offer this whole adjust for the project to everyone, and we all will go through it slightly. And today's day of John. Based on what is written in your homeworks, it will be mostly near and dear to his winning mathematical side. So the narrow goal is to see mathematical proof that oscillators exist. And we are going through tons of excessive abstract concepts, which could be a little too much for this simple statement. But at the time when these theories were developed, the researchers were happy and joyful that there is at least few problems that can be solved exactly. So we formulated our approach to oscillating oscillator to get oscillations oscillator through the concept of eigenstate of annihilation operator. And we did practice this annihilation operator in form of matrix on the basis of eigenstates. Right? And after establishing the two series, I was watching recordings. I should do this. After adding these two, making sure that these two series should be equal, it will be equal if their elements at appropriate indices are equal. And it looks like connection between this senior and junior are connected through recursion. But if one knows lower order, one can get higher order. When we practiced this recursion and normalization, we came to a solution that eigenstate of annihilation is a summation with this series, expansion coefficients of all eigenstates. The series slowly grow at the beginning but then drop radically. There is normalization, and the annihilation operator does not create this connection. Therefore, expectation value of annihilation operator is not constant. And through the manipulations with eigenstates, each of which accumulates phase, the higher the stable, larger the phase, one can transfer the phase from eigenstate, phase accumulation from eigenstate to the from eigenstate of oscillator to expansion coefficient of eigenstate of annihilation plane. Then if you make this symbol, this series time dependent, then we come to an idea that because the powers here of mu and the exponential there are the same, it looks like the mu thing is just oscillating with the frequency of oscillator. And then we went to space representation, changed the letter mu to the letter gamma. Right? I didn't erase it, still there on the plate. And you already got the solution, but for harmonic oscillator that has been prepared in a quantum state, which is an eigenstate of annihilation operator. The coordinate distribution in coordinate space is Gaussian function where the center performs cosine oscillations with the natural fundamental frequency of oscillator. Right? So we covered three lectures. What else we may want to do? Are we already happy, or there is a little bit more of mathematical flavors related to oscillating sleep? In sense of satisfying physical chemistry curiosity, we do not need more. We are already happy with this notation. But if you want to practice skills and concepts that we did before, with the hope that maybe some of us will need it in either later chapters of the course or later chapters of scientific life, we may try to explore Heisenberg equation of motion in respect to harmonic oscillator. We skipped Heisenberg equation of motion for particle in the box, but we practiced it for free space when we needed position as function of time. Here we already have the position as function of time through differential operators and some calculus manipulations. But we may check if our previous lecture was a waste of time and the same result can be obtained in shorter approach. I will have slides to cover it, but I'll give heads up. Due to the last homework, which you all performed well, but some of you performed elegantly. You may have noticed that by making annihilation of by making commutation of annihilation of Hamiltonian, it's like general audience will not understand a single word. Commutation of annihilation is Hamiltonian. One gets annihilation operator back, which means that it prompts that one can set up Heisenberg equation of motion for annihilation operator, and it will be first order differential equation in time that is easy to solve. So the plan will be that we will get Heisenberg equation of motion for annihilation, symmetric Heisenberg equation of motion for creation, and when we add them together, they will generate position. Expectation value as function of time. So basically, we are going to get the same result, but from more advanced and elegant concepts. There will be no big surprise. Amount of mathematical effort is approximately the same. Last lecture, but it's two alternative methods, and harmonic oscillator is one of the systems where both of them work. But there are a lot of situations when one works and another doesn't. So I promised myself to update this figure from year to year, but I failed. So we do have three-dimensional space of theories and models. On the x-axis there are theories, and we do have time evolution, Schrödinger equation in several forms, depending in this case, Heisenberg equation of motion. Then as a concept we got the density of states, and now we got the ladder operators and then Heron states. So, we are poor in applications, but we are rich in methods. And for applications, we started with free space, and we didn't practice each method for each system. For free space, we have evolution. For one-dimensional box, we saw tree equation. For boxes, we more dimensions, we practiced density states. And for harmonic oscillator, we should have solved Schrödinger equation. I was resisting this any way I can. So instead of solving Schrödinger equation for harmonic oscillator directly, I was really on a path that seemed shorter to me, but you may be irritated. Why should we bypass a very straight path? So we used ladder operator and Heron state as a shortcut to solve Schrödinger equation. And today we will see what can we feel in this space. I'm going to split it by the Heisenberg equation portion. So if stars will be in the right arrangement by 32 minutes, we should arrive to this. So it is very similar to what we just got, what we discussed already, but this one is in one aspect is lighter, and another is richer. So I will not jump forwards and backwards in slides, but when we were looking at the probability distribution that moves forwards and backwards, and the expectation value has sign oscillations, we assume that it starts at most elongated phase. And potentially we could tune it by changing the rho, by changing the initial phase. But it was not quite elegant in a sense, not universal. If you already know that we have expectation value of this vector elongated or contracted, and we want to predict future, there were no direct way to put it there. Also, the solution for coherent state was limited in the sense that we were talking only about eigenstates or conjugation period. There is no theorem that harmonic oscillator takes only those states. It can take equilibrium eigenstate, it can take oscillating coherent states, but it can be anything we construct. So in some sense, it was not universal. What we are going to obtain today is through the application of the Heisenberg equation of motion to oscillator. We're going to get, well, if I consider just trying to spend and sit and plus to the lunch, it doesn't matter. But if I like organized logical solutions, which is not typical for medicine. Then this solution looks beneficial because it takes initial value of position, expectation value of position of oscillator as an input. It also needs expectation value of momentum of oscillator as input. As a result, after this simple math, it generates position momentum as function of time. And it will be if momentum is originally 0, and you have only position, then row by column you give cosine oscillations to this exponent, right? But there are more rich general situations when, for example, we start with 0 position and non-zero momentum. No one tells us that it's not possible. Just see the equivalent, or maybe both, deviate from equilibrium or whatever. So it can be both factors will work. And if one plots this solution on the diagram with expectation value of position momentum, it will do so. In some sense, this result for harmonic oscillator will not differ from what one would get from classical mechanics. No quantum theories at all. But we discussed Bernfest theorem. In some cases, classic quantum solutions will produce classical results. And it's not good or bad, it's just useful reference point. Position is 0, momentum positive. Then position will start to increase, momentum will expect. Then come to the turning point, then position will start to decrease, going back, momentum will come 0 and then negative. So, okay, if you don't care about math details, then basically we are done with the lecture. If you agree to listen to a little bit of derivations. You remember this equation, right? It's like a bridge between the abstract function and observables. You already did this exercise before. It was part of your homework. If one multiplies equation and integration together, there will be summation, and one needs to have the indices different. And then there will be 4 vectors, 2 bright, 2 cats, and the middle one will convert into a delta function, and with the outer one will remain. Because of this delta function, the indices will find that they need to be the same. Then one can also change the counting from n plus 1, the first n plus 1 is k, and then the Hamiltonian can be expressed as diagonal matrix with number of excitations in fact. If one performs the same, no, there is a little trick that it was not part of the problem. You can do it, and you probably had a suspicion about it. But let me focus your attention. There is a little change, right? here we swap the order of this operators. And then if you do again the trick of making the delta function with insider bracket, then the indices arrange in a way that indices here and there are the same, but they differ from what is here. And, it means that previous matrix that integer number on the diagonal, this matrix also has integer number on the diagonal, but it is by 1 individual. Previous go 0, 1, 2, 3. This one goes 1. Why do we need it? Because it happens. I don't have better explanation, because when we practice Heisenberg function, we need to practice co-mutation of operators. And if Hamiltonian is a dagger a with some factors, then we will have this a minus stuff. And we need to take care of that. Just a little exercise relates to the accomplished homework. If you multiply the one with dagger at the end with the one with the dagger at front, since the indices are different, but indices are different, but their difference, subtraction is the same, independent of the number, right? So it would be a matrix with number 1 everywhere. And you already got it or saw it, or it was part of the homework or some preparation steps for it. So the it was an input that you were using. So commutation of these operators gives to unity matrix. What changes if one swaps the orders of the operators in the commutation? Huh? Exactly. It's I'm pleased to hear. So it will be either plus or minus 1. And these all are preliminary preparations. Now, the Heisenberg equation of motion is commutation of Hamiltonian operator of interest. And if you need expectation values, put this pink bracket. So you would not object. And then if you need to find commutation between Hamiltonian and annihilation operator, by the way, you can remove this 1/2 because it will be in both positive and negative side, and it will be subtracted. So there will be 2 terms, a dagger a first term, and second term will be a dagger a, and you already got it in your homework. It is because of the commutation, it should be negative, right? Catch me wrong. And there is a frequency upfront from the Hamiltonian. If we do the same exercise with a dagger, we will get this a dagger back with frequency and with plus sign. Anyone objects? If needed, you can repeat it, right? More or less, it's not a big change. We are done with, not with large field, but with mathematical challenges in some sense. The rest is maybe there is a little effort, but it is more practical and conceptual. Does anyone wants to object this equation? Or should I explain what it is? So for dynamics of operator, we need a commutator. We just show that and then imagine a unit and some constant come up front, but here when it's a direct commutator there were minus h per omega, so h cancel. And we will need to put brackets right at the expectation value any time, but I was just lazy. So this is the thing that I wasn't when I was in the undergraduate years. Many things in instructions and lecture materials were irritating. This one was not at the level of irritation, but it was a novel concept. I was resisting to accept that one can solve differential equations for operators, not for numbers. So it is much easier for human to accept it if one put brackets. But formally, no one forbids to solve it with or without this brackets. So if we divide left and right part in independent, I would like to say variable of u is operator and multiply left and right by time derivative, then everything on the left depends on independent thing, and on the right it's a constant derivative. So in this course we do not do anything more complicated than the first order differential equations. So logarithm and linear type, right? And if you do not like logarithm, you can take both left and right parts and power exponential. And then finally, one day you need to put brackets, so the expectation values of annihilation operator will be initial condition, which is expectation value at time 0, and then just this accumulating phase factor, as we already got in most any quantum problems. Right? All clean, right? No manipulations. So from commutation we get that expectation value of annihilation operator oscillates in complex phase, in complex plane. What do you expect if we perform the same practice for the equation operator? You can guess the answer. So if this one oscillates with complex phase with negative angle, right? Moving phase in negative, what based on commutation, what should be? It should be again oscillations, but this should be the same or different sign. Okay. So they will be like two clocks rotating in the opposite direction.
Does the cosine change to sine then, or is that?
Where is the cosine? It's constant.
Okay.
We are opening the session of club of probability defense. Constant. C-O-N-S-T. I can even do it. Do you see any connection with what you were doing 2 lectures ago? And it was briefly reviewed today. If we are looking for eigenvalues of annihilation operator, so it's summation like that, and everything that stands here in the under brackets and under power n is eigenvalue at time 0 times exponential accumulating phase in the negative direction. You see it? Do you see any connection between our recent finding into the expression that we did last time? Do they differ? Or are they the same? Okay. So, in some sense, we did obtain the solution for time-dependent eigenvalue of annihilation operator. So expectation value of annihilation operator and eigenvalue of annihilation operator coincide. Just happens. There are no immediate consequences, which is an interesting observation. And if one performs the same protocol for creation operator, it will accumulate phase in the positive direction. Here is an assignment for quiz that I suggest to cancel because I would make an error in these factors. But the principle is that annihilation and creation operators can be defined mathematically as summation or subtraction of position and momentum operators, right? And if this is correct, the inverse transition is possible. And position and momentum operators can be expressed as summation and subtraction of creation and annihilation. So we add together creation and annihilation, put the right factor to have the dimensionality. And we get position over time. So in some sense, it is what we need in 12 minutes by the end of the meeting. So we need position as function of time, and we decide to express it in terms of summation of expectation values of creation and annihilation, which we just found based on commutation. And initial values and accumulation phase to the left and to the right. This. And I'm so lucky that it's already prepared and I do not need to do right. I'm not right all the time. In some sense, it is one level of recursion. So the position as and I invite you to look in the first line. So here the position operator is the factor with time mass frequency. Oscillating initial values of creation and annihilation operators. Creation and annihilation operators, especially at time zero. Time zero is better because it doesn't have time dependence. Creation can be expressed as subtraction of position and momentum. It looks like a little crazy thing. I want to express position as function of position. With annihilation and creation operators are intermediate concepts, right? So the linear transformation of position, momentum, and creation and annihilation works both ways. Now I apply both of them. Creation is summation of creation and annihilation, and creation is subtraction of position and momentum with all factors which you need. And here it is summation of position with those factors. In this expression, there are 4 terms. 2 terms proportional to position at time 0, and 2 terms proportional to momentum at time 0. Is there a chance to slightly simplify this expression of moderate level of ugliness by adding together everything that relates to initial level of position in one term, and everything that deals with initial level of momentum with another term? Possible. Probably we will get a bit tired if we try to write it step by step, but there is no big challenge. And then if we add the major challenge is just carefully processing the factors and of these fundamental units. But the rest here it will be exponential revolving in positive direction plus exponential revolving in the opposite direction. Right? And for the terms in front of momentum, there will be negative and positive exponential is negative factor of factor. Negative exponential is positive factor of factor, meaning subtraction of 2 exponentials revolving in different directions. Who teaches us how to deal with such exponentials? What's the name? Huh? Okay. What is being taught to us by Euler? So the summation of oscillating complex exponentials is replaced by 2 cosine, and subtraction of 2 oscillating exponentials is replaced by 2i sine. Interestingly, when we did this transformation, there was imaginary unit here up front before the momentum, just for definition. But if you practice Euler equation, the imaginary unit comes into here, and then 2 imaginary units cancel each other, and then the overall expression becomes real. Are we done? We need to wrap up. Okay, but in fact, we have everything we need. Our goal was to find expectation level position of oscillating oscillator. And we wanted to make it more logical and useful for practice, and someone doesn't know how oscillator to input the initial position and initial momentum expectation levels. And we got it. We put initial position and initial momentum, and through the sine cosine we get the answer. It just looks ugly and not useful for immediate processing. Something can be concentrated in the evaluation. I'll better stay on the previous slide because it was typed in more beautiful. In some sense, there are product of initial position and all factors, which can be initial momentum and all factors. And in some sense, one can express it as row by column matrix. Row of constants by column of initial position and momentum. Through analogy, you probably will not be surprised if we assume that this same procedure can be done for initial momentum because they are companion variables. And if one does the same thing for momentum, I think it is skipped from the slides, but perform the same procedure of expressing momentum via creation and initiation. We plug it creation and initiation as initial position of momentum. When we will get connection between when we will get expression for momentum as function of time. And it will be also possible to represent as product of the coefficients, which are time dependent, and initial values. So how momentum evolves in time also depends on position. And then if we keep into account that they both are conjugated variables, and it makes sense to treat them simultaneously, then this further position and further in time will be proportional, not proportional, will depend on initial on the values of time zero for this say, it's not evolution matrix in the sense of evolution operator, but it's same idea. There is a vector at initial time, vector at final time, and matrix that transforms. I think we are approaching the speed end. If one wants to plug in numbers, assuming that mass and frequency equal 1, then sine and let's look on a we already looked at a situation when initial position is maximal and momentum is 0. Then contribution from the second term is nothing and it will be just sine oscillations. At the same time, if momentum is 0, but position is not 0, then row by column will get that momentum will oscillate as negative sign, which means it starts from 0 and then it will negative. So if we put 1 here, 0 here, and put all constants as 1, then we will start from this red button, and position will be oscillating as sine, momentum will be oscillating as minus sine. But if we format it fully, it will be circular trajectory. What should we tell that it is waste of time, or our previous lecture is waste? It's an analogy, but what is superior in this approach compared to the previous one? Can we have, do we speak anything, do we discuss any about functional form of the wave function? So this solution is universal, even if the initial, you have already seen ugly wave functions, right? If you run our wave packet code for a long time through accumulation of errors, it does something crazy. So if your wave function is neither eigenstate, neither a HO-HEOM state, nor neither the theory of a HO-HEOM state will not work in position as function of time. But this state doesn't preclude one to practice this operation. So one just finds the initial position. One can find momentum by telling how to find expectation values, but there is a subroutine in the code. One can set up the find initial momentum for just practice it by pen and paper, and plug them into there. And they will oscillate in this way, even if the wave function is this one or even other. So it will be universal. No matter what's the shape of the wave function, it will obey this solution. If the both initial position and momentum, it is a symmetric function, not necessarily ground state, just eigenstate or something symmetric, then both initial position and momentum will be zero and it will not change. But, there are pluses and minuses, but one of the pluses of this equation that is universal. Thank you for investing your time on Monday morning, and looking forward to see you on Wednesday. But do you know new regulations about the Thanksgiving? What is our schedule?
We don't have a class.
Huh?
We don't have a class.
No class on Wednesday.
Or Friday.
Okay, so next week we meet only on Monday, and we are missing our lab.
Yeah.
Have a nice day. And see you next week.